I'm going to start this video with a couple of slightly different descriptions of the concept of pressure. One of them is pressure is weight divided by area. So if you have the weight of the atmosphere above you divided by the area. The other one is a microscopic version of pressure, and that is where you have the sum of the changes in momentum over time. That is the force uh, divided by the area. And this is like more of a microscopic description of it. Let's see, what did I say here? This is kind of hand waving, but changes in linear momentum in the z direction. That's why it says delta v sub z contributes to the weight. The 2 in the 2 over degrees of freedom is based on the fact that the bounce is twice the velocity. The dF in the 2 over degrees of freedom is based on the fact that only one of the degrees of freedoms actually contributes to the temperature. For the sake of symmetry, we're making that the z direction, the linear component of the velocity in the z direction. So I've been looking for a path description of del p del z, del t del z, del rho del z, but based on the preceding principle, I think we can definitely state that del p del z, based on the weight over area term, the weight is mass times gravity, mass times gravity divided by area divided by delta z is here. So mg is weight over area times delta z. I should have put it that second because the density is mass over volume. Okay, now I got the steps of the derivation in order. Del p del z is the negative of the weight over area over delta z. Weight is mass times gravity. Area times delta z is volume. And mass over volume is density. So we got del p del z based on the idea of the weight principle. We've got a value of del p del z equals negative rho g. But we can also get it from the falling principle because this m delta v sub z over delta t, I can just take that delta v sub z delta t and turn it into a del squared z del t squared. And then this sum of m is density times volume. So, and this a delta z down here is also volume, so I can cancel out volume with volume, and then I get rho times acceleration, so it's negative rho times g again. So we've got two different equivalent derivations for representing that del p del z is negative rho g. So I think we can confidently state that this is dp dz is negative rho g. That is the total derivative of the quantity. But I should point out that that in no way implies that g of z or rho of z are constant. It just means that at a given point where g and rho are known, this differential equation will hold. But then I still was earlier. I was concerned. I felt like there potentially could be an argument to be made that the formula for the fall was inaccurate. In particular, there's the use of this dt variable here, and I was thinking there were two different possible, that delta t was being used in two different ways. Is delta t the time of collision or the time from the beginning of one collision and the next? Or the time between a collision with the top surface to a collision of the bottom surface? I think it's actually the last for both cases. dt is the time between the collision with the top and the bottom surface. And dt is also the time during which the particle is in free fall. So it is actually the same time for both dt's. And then dz is the distance between the surfaces. And so with all that in mind, it seems incontrovertible that d squared z dt squared is equal to negative g. Was there another concern? Yes, another concern I had was in regards to the modes of motion, and I'm concerned about whether the gravitational potential might somehow be converted into rotational or vibrational energy, whether that could affect the pressure. I think, though, I like to come back and reuse diagrams a little bit, but I imagined a diatomic molecule falling. It increases the linear kinetic energy, then it collides with something set into a spin. But I think what happens is that spinning motion actually does contribute to the pressure. Because if this particle had been spinning, then when the collision had happened, then that energy from that spin would have contributed to the pressure as well. So in this particular case, I think we still, even if there's spinning involved or vibrational kinetic energy, I still think that this total derivative dp dz equals negative rho g is going to apply. So here's a little summary where I have put this partial derivative. That's essentially true, but I want to make it more general and say that dpdh is negative rho g. So it's the total derivative of pressure with respect to height. Then I also derived this dtdh and del t del h. I'll review that formula. It came from assuming that the internal energy of the gas was proportional to, or was equal to, the density of the gas times gravity times some h sub z minus h. The n here was the density divided by the molar mass, and then just solving that for t and taking the derivative with respect to h. And I think there's not really any reason here. I don't think there's any reason here to put this in the form of a partial derivative either. So I can declare that to be a regular derivative instead of a partial derivative. Now what's interesting here is that mu, g, and c sub v are all definitely properties of the gas. Let's look at that. Mu is the molar density of the molar mass of the gas. G is the gravitational constant, and c sub v is the specific heat at constant volume. And actually, I've gone to the trouble of plugging in those numbers here. Mu is 0.02987 kilograms per mole for air. G is 9.8. The specific heat at constant volume for air is 29.07. This actually comes out to be 0.009766. One might write this as 9.76 Kelvin per kilometer. So there we are. So now I can finally get back into section 9 of planetary core and surface temperatures, where he says, using data for Earth, we calculate a gradient of 9.8 degrees Celsius of warming for each kilometer of reduction in altitude, and vice versa for cooling. Because I actually did just calculate dTdH equals negative mu g over c sub v, and those values came out to be 9.76, very close to 9.8 Kelvin per kilometer. Now, by the way, we haven't really done a terribly good job of actually predicting the temperature versus altitude curve here, but it's in the right order of magnitude here. It appears that we go from about 15 degrees Celsius to minus 55 degrees Celsius, somewhere around here, in 100,000, or sorry, 10,000 kilometers, in 10 kilometers or 10,000 meters. So it's going where we predicted 98 or almost 100. It's actually going down about 60, 70 or so. Okay, so presumably the sun heats up the ground to a temperature of wait a second, it wasn't minus 15, it was positive 15 degrees, right? Positive 15 degrees. Heats up the ground to positive 15 degrees, and that heat is at the 0 altitude level, and the temperature should, if our equation is right, what is it? dt dh equals negative mu g c sub v. Of course, since this is got h over here and t over here, it'd be dh dt equals c sub v over negative c sub v over mu g. That's the way that slope is right now. But let's say, but we don't have this. What we have instead is something like, what did the temperature go up to? Okay, the temperature at 10,000 feet was about minus 50. So I will put minus 50 in my graph. Okay, so there's the minus 50 line. And instead of reaching minus 85 at 10,000, we are going to reach minus 50 at 10,000. What phenomenon might explain that instead of having dh dt equals c sub v over mu sub g, we have a steeper quantity, that there's actually more height than that? Well, what I would suggest, just a possibility, is that there is energy incoming from the sun energy incoming from the sun that is heating the atmosphere. Yeah? Possible, maybe. Maybe there's a little bit of energy coming in from the sun that's causing the temperature in the atmosphere to be a little bit hotter than would be predicted by just this equilibrium case that dt dh equals negative mu g over c sub v. Maybe. By the way, there is also still to be explained why the surface temperature down here is 15 degrees Celsius instead of negative 19 degrees Celsius. Because, remember, Stefan Boltzmann's law predicted that this temperature would be close to negative 19 degrees Celsius. So that's an important element of this too. And that might be due to the fact that maybe, just maybe, there was some time when the surface was heated to negative 19 degrees Celsius, and then heat tried to escape and hit the greenhouse gases up there, and didn't get out so fast as it would have liked to. So it came back and warmed the earth. Maybe. And he actually says right in here, the amount of water vapor and other radiating molecules like carbon dioxide reduce the absolute value of the thermal gradient. So basically right there, he just said it. He just said that carbon dioxide does what I just said. It it reduces the gradient of, it reduces dTdH, but in this graph, the way it's drawn here, it's increasing the absolute value of dH dt. So, but that is reducing the gradient of dTdH. So it is it's basically heating the atmosphere when it reduces the gradient. Because we saw, based on the logic, that without greenhouse gases, we would have had dTdH equals negative mu g over c/v, which is right here. And with the greenhouse gases, boom, we get a more heated atmosphere. Okay, so he's graphed it on the other axis than us, and he says that the overall mean level of the plot is determined mostly by the intensity of radiation from the sun, adjusted for reflection and some other factors. So what I'm going to do is just kind of turn the plot sideways, because he's putting it graphing. But yeah, it's like the amount of radiation coming in will, I kind of even drew the arrows intuitively, as though they were coming sideways into the system. I don't know why, because it's not really that variable. But anyway, yeah, increasing the amount of energy from the sun into the system will increase the mean value. It'll also increase the slope, the absolute value of the slope. It says the plot moves up and down through parallel sloping lines if the insolation, as it is called, varies up and down, as can happen in natural cycles, which may relate to variations in solar intensity. Okay, so I think what that means, if I actually moved this thing and if I actually moved that thing, kept it parallel, what would happen? If I moved it back this way, it would make it so that the ground temperature was, say, 25, 30 Kelvin. So if this thing moves up this way, then you're going to have a 30 Kelvin temperature at the ground. So I'm not sure what he's finding comforting in his description here. The plot moves up and down through parallel sloping lines if the insolation varies up and down. Oh, he's just saying, oh, he's trying to make the case that the insolation would change, rather than worrying about the so the amount of light coming from the sun, he's saying, if the amount of light coming from the sun moved up and down. So for instance, if you compared Earth versus Mars versus Venus versus Mercury, the amount of insolation coming from the sun would be different for those different planets. And he says what this all comes down to is the fact that the temperature level at which the predetermined plot intersects the surface is itself predetermined primarily by the above-mentioned parameters, and not much of any great significance. Water vapor and, to a much smaller extent, carbon dioxide radiate heat to higher levels, never transferring heat to a warmer region or surface, and so they reduce the gradient and also reduce the surface temperature. So he's I don't think I've ever heard, I don't think he has mentioned Stefan Boltzmann's law in this so far, but he's saying the fact, or the temperature level at which the predetermined plot intersects the surface, I gather what he means is that you might change this, you might change that slope, but you're never going to change this point, this 15-degree point where it hits the surface. And I guarantee you that's false, because As long as, if there were just transparent gases in the system, then all of this light would come in, be absorbed by the ground, and then be re-emitted, and the carbon dioxide, water vapor, and methane would not absorb a single bit of it, and the surface temperature would be about negative 19 degrees Celsius. So the reason that it is positive 15 degrees Celsius instead is because the heat gets stopped by the greenhouse gases on the way out. So he says, so gravity in dry conditions creates a steeper gradient, but the water vapor reduces it by about a third, bringing the surface temperature back down to the observed levels. I think what he's imagining is like putting the fulcrum up here at the surface of the atmosphere rather than at the ground, so that and then he's imagining that somehow the water vapor creates a steeper gradient, but then gravity somehow brings it down to here. I don't know. I don't think, I'm not sure I can make any sense of his argument, but I will see if he explains the greenhouse conjecture correctly. He says, but this cooling effect of water vapor is the exact opposite of what is claimed in the greenhouse conjecture, namely that water vapor warms and has a positive feedback, supposedly amplifying this assumed warming effect of carbon dioxide. Exactly, yeah, because we assume that the heat comes from the surface instead of from the, and we assume what do you call it? We assume Stefan Boltzmann's law at the surface of the planet rather than at the surface of the atmosphere. It says a brief study was carried out by the author to see if temperature records in real cities in the real world confirmed any warming. The study is in the appendix in this paper, and the conclusions are that there is no evidence of any warming, but instead an indication of the cooling which was explained in the last paragraph above. I can't do the rest of this chapter. Some of this stuff sounded right because this part seemed right. If you imagine plotting a graph of the temperature against the altitude, the slope of the plot is predetermined by gravity, specific heat, and the amount of water vapor and other radiating molecules like carbon dioxide, and those radiating molecules reduce the absolute value of the thermal gradient. And I agreed with that. I was saying, okay, here is what is predicted by gravity. You add some carbon dioxide and stuff like that. That reduces del T del H, which increases del H del T, so it brings it up to there. I agreed with that statement. When you add carbon dioxide, it reduces that slope. I mean, it actually increases that slope, but reduces the del T del H. And then he said the overall mean level of the plot, determined mostly by the intensity of radiation from the sun, adjusted for reflection and other factors. And I did feel like if we adjust the radiation from the sun, then the graph should slip this way. So like this would be Venus, Earth, Mars. So depending on how much radiation is coming from the sun, it will slip to the left or right. And this is the sentence where he was not correct. He said, all this comes down to the fact that the temperature level at which the predetermined plot intersects the surface is predetermined primarily by the above-mentioned parameters and not much else of any great significance. This is where I completely disagreed. I disagreed because I say if we had a completely transparent gas here, then this would be our line, and it would intersect the surface at negative 19 degrees Celsius. And that is where it would be if we had a completely transparent gas. If we had a perfectly transparent gas, the heat input on the Earth would be equal to the heat output. This would be where the equilibrium was. It would be based on, and I'll go through that derivation real quick here. The intensity of light coming from the sun is based on the power of the sun divided by the surface area of a sphere with Earth-Sun radius. Comes out to be about 1,369 watts per square meter. But then the cross-sectional area of the Earth is pi times the radius of Earth squared, which is about 6.37 million meters. This is the albedo of Earth that tells us about how much of the sun's rays are just reflected off without adding any heat to our system. And then, where did that line go? Okay, and then the power coming in is 1 minus the albedo. That's the amount absorbed. And then we have I times Earth-Sun. That's the intensity from the sun times the cross-sectional Earth area. So that's the power coming into the Earth. And then we figure out what is the outcoming area, which is the surface area of Earth. So that's 4 times the cross-sectional area. And then the temperature, this is a use of Stefan Boltzmann's law. So the temperature is the 4th root of the power over area times, and then sigma here in the bottom. And then I'm just subtracting 273. I'll subtract 273.15 because that is more exact. That's the temperature of 200. That's the 0 degrees Celsius is 273.15 Kelvin. So this gives us the temperature of the Earth in degrees Celsius. That would be the case if we had no greenhouse gases. Now I've written that down here as negative 19, or well, minus 20. This is what the atmospheric temperature versus height graph would look like if we had no greenhouse gases. We'd move it over and slope it up. Since we do have greenhouse gases, this is what we've got instead.